All right, time for another draftphysics.com, debatephysics.com also. And in consistent with debate, I will make some of these argument videos. So arguments that convince me certainly that momentum is all there is and that kinetic energy is a fable, that there is no such thing as 1/2 mv squared as a real property of any real thing in the universe. And there are simple experiments that are rather decisive in the evidence they produce, and there really isn't any reasonable counter argument provided anywhere, anything I can find anyway. So, in that vein, we have something as simple as the lever, and the fact is you can convert it into what we call a balance. So, let me just find where I'm allowed to draw here. And so you have a simple device, and you're going to put a fulcrum on that simple device. That is, you're going to put a center point, and you're going to have the same mass on both sides, and the stick will oscillate. Okay, so if you push it one way, it oscillates and goes the other way. Now that's a balance. If the fulcrum is here at the base, it won't balance. If the fulcrum is up here at the top, it will balance. And if it's in the middle, okay, you'll get a circumstance where you can put equal mass to distance ratios on the lever, and they will stay balanced no matter what position you put them in. So the idea is, if you make the lever thicker, is you could understand, okay, that what you're really just doing is changing where the mass is. So say if you did have a fulcrum here, and you tipped the lever up in this direction, you could understand that now this straight line goes through, and what you've really done is put more mass on this side of the lever, right? The mass that was over here, all of this, is now over here. Okay, over here. Just put a little X there. That's not exactly beautiful, is it? But anyway, you'll have to do. So what you're doing is, as you tilt the lever, as you move the lever down, more mass is on the side you're moving down, so it just becomes heavier and swings all the way down. Now in the middle, okay, so if you have your fulcrum perfectly in the middle of the weight of the lever, then that doesn't happen, in the sense that if you're in the middle, I should be able to just slide this up and over. Yeah, that you don't need. Yeah. Anyway, I should have taken a clean piece of paper. Duh. Alright, so if you have the fulcrum in the middle, you can understand that you're going to do is both, you're going to have mass on this side when you tilt it, and then you're going to do a compensating mass on this side. So the two will equal each other, so you won't unbalance the lever. And what you're really showing is that as you can have the two mass here on the lever, and you can have a one mass way out here on the lever, twice the distance, and those two will perfectly balance, indicating that twice the velocity on this side for the one mass is exactly the same as one velocity for the two mass. Kind of a decisive. And again, so then if you put the fulcrum below, okay, the mass, as stated before, you can understand that as it tips, it puts the extra mass over there. So suspended from the top, it does. That's the one I haven't done yet. Okay, so suspended from the top is the one we're supposed to do. All right, so if you suspend it from the top, the exact opposite of what you did with the bottom thing happens, in the sense that instead of you pushing, so when this tilts this way, if I tilt it down, alright, what's happening is now I'm doing the opposite. I'm taking mass that was on this side of the lever and I'm putting it over here. So now it's on this side. So for every bit I go down, I push more mass this way. So as I push down on this side, I push more mass that way. That way there's always gaining mass. So the further down it goes, the more mass is on this other side, which means there's more gravitational pressure, means it wants to oscillate. It wants to go back in the other direction. It'll use up the energy and then swing back in the other direction, and do the same thing on the other side, and then swing back, and it'll oscillate. Okay. And I've demonstrated that experiment on my own porch many times. well, one time that matters. Yeah, so, all right, take a pause and get another piece of paper. All right, back. Didn't just need to flip it over. Anyway, okay, so there's three positions, and this basically converts a lever, okay, the traditional lever, into a balance. Is just the location of where you're applying the counter force, the stopping force. So if you apply it at the bottom, then no matter how you change that, you can put two balanced weights, but it's very delicate. And as soon as one side gets any motion, it'll swing all the way down. So it's not a good balance because it's all or nothing. Then from the middle, the same kind of deal, at least it'll balance in any direction. That is, you could put a two mass, 1 unit of distance, or one mass, 2 units of distance, and the two will show that they're balanced. But any deviation, any creation of any energy, and it will swing all the way down. So if you increase the mass of the two by just a tiny bit, it breaks the function of the lever, or the balance in this case. And then you have the balance position, which would be from the top or from some place high above the lever. You can use chains or some other mechanism to make the balance even more balanced. Okay, that is, swing more mass over to the other sides. This one will allow that for every bit of any deviation will just cause a swing in the balance until the deviation is compensated by an equal mass being swung over on the other side by the lever. So it's a constantly compensating for any mass differential or action or force differential, and it will oscillate and show that two things are the same mass. All right, same force to move them. So the only thing you're doing, so when you're using a lever as a balance, suspended from the top, the only thing, let's say I do put the two mass here, and I put the half mass twice the distance, okay, and I'll get a perfect balance in that it'll stay perpendicular, because any motion down will push extra weight onto the other side and cause it to balance that and bring it back up. So any motion is going to create an oscillation in the lever, a balance that'll take time for air resistance and whatever little tiny bit of friction there is to use up that energy, so it can oscillate for quite a while like a pendulum. And it just basically proves that the masses are, in this case, they're entirely irrelevant, and the only thing you're really doing is shifting a piece of matter here in the middle, this mass in the middle, and you're just shifting its position from one side to the other side, and that's all you're doing. So if this goes down, the mass goes over, it compensates. If this side goes down, the mass slips over to the other side. So it's the same amount of mass that's just moving from one side to the other side. So you can just think of it as a little piece of matter that's just going from one side, and then it pops to the other side, and then it pops back to this side. And that's all that's oscillating. So whatever oscillation I create, so I start the lever from, it's balanced. So it does prove that the two mass equals the one mass at twice the velocity. And the reason why it's only twice the distance for twice the velocity is because gravity isn't really having an effect. It's just showing you that the amount of gravitational force to move this object is identical to the gravitational force required to move this object twice the velocity. And so it's basically just proving the case that the two mass at one velocity is exactly the same energy as the one mass with, that's a little annoying. Jesus Christ. Either too much light, too little light. Just can't seem to get something more perfect. All right, anyway. So what I demonstrated on my porch was actually the 4-to-1 relationship. So I put 4 objects down here. All right, dangling from the one position here. magnets, and 1 out here, 4 units of distance out. So it was actually 4 times. And the kinetic energy theory argues that this is 4x the energy here, because it will move 4 times the velocity. That is, the amount of distance it moves in the same time will be 4 times, will be 4 times that velocity of this motion here. And so it basically demonstrating that if the kinetic energy theory were true, there would be 4 times the energy to move this object than there was to move this object. And the fact is that this same piece of matter moving from one side to the other side is proving that the same mass here moves this, and the same mass here moved on this side moves this. And so it's just basically proving the inequality, that the same gravitational energy placed on an amount of matter is producing the energy to lift this back up, and the same is true over here, that the same gravitational energy to pushed down on this little extra bit of mass on this side of the lever pushes this one back up. So it's basically a pretty solid proof. Yeah, I don't love that drawing. It's just a little still out of focus. Just can't fix that. My finger's not terrible, but anyway. Well, whatever. Maybe I just need to draw. Maybe I can move it further and then draw bigger. Yeah, we'll see if I can do that. Anyway, yeah, that'll help. Alright, so it's a video anyway. So just making the point that the lever, no video I've seen explaining leverage or balances goes into this subtle detail that if you have the fulcrum down here, it won't balance, because for every bit of motion this way, more mass ends up getting slid over to this side, and so it just makes the mass heavier and it swings down. Or if it's in the center, then you've negated that problem, but you still have the problem that any action in a direction is uncompensatable. You can't compensate for it, so any action causes a reaction and causes motion, and that motion, there's nothing to compensate for. No extra mass is being placed on the other side to balance against whatever force you push it. So it'll stay here, it'll stay here, it'll stay here, but if I move it, it'll just go spin like there was no masses on it at all. It'll just spin like a common wheel. Now in that case, it is proving that if you have the 2 mass attached and the 1 mass twice the distance, it will prove that those 2 are the same, because it will spin just fine. And then the third case is the balance case, where you suspend it from the top, and that way every turn this way throws more mass on the other side of the straight line and makes this side heavier, and so it swings back. It compensates for any action on one side is compensated by a movement of mass on the other side that forces it to go back. Yeah, so that's pretty much it. And all 3 cases, well, 2 of the cases essentially do prove that the lever is overtly saying, the balance is saying, that a 1 mass moving twice the speed is the same as a 2 mass moving half that speed. Same thing. And that a 4 mass moving 1 unit of velocity is the same as a 1 mass moving 2 units of velocity. 4 units of velocity. Yeah, sorry. Oh, see, you shouldn't make mistakes like that, right? Oh. Okay, but anyway, so it's that the momentum is completely the rational theory, and kinetic energy can make no sense of it at all. So there's no defend kinetic energy using a lever. Explain how a balance or a lever demonstrates the truth of kinetic energy, because in my opinion it's a decisive, complete proof that it can't possibly have anything to do with reality. Alright, enough of a video. Probably have to do it over just because it, blurry drawing. Yeah, the argument against is your drawing's too blurry. Okay. Anyway, till next time and such.